Okay, hi everyone. One last topic that I want to talk about this week, and I hope it's one that many of you are familiar with. It concerns the temperature dependence of rate constants. It's described in Atkins 17D. The starting point is this observation right here, that reaction rates, and therefore rate constants, are strongly temperature dependent. So this is an example for the decomposition of an aldehyde. So starting at 700 Kelvin, if you increase temperature to 730, like a 5% increase, it goes up by a factor of, the rate constant goes up by a factor of 2 or 3. You go up by another 30 degrees, so you've increased it 10%, and the reaction rate has increased by an order of magnitude, right? You go up another 10%, and you're up 2 orders of magnitude. You go up a 50% increase in temperature, and you're now like 3 orders of magnitude increase in the rate constant. Right? The rate constant goes through the roof. They're strongly, strongly, strongly temperature dependent. And the person who first described this behavior was Arrhenius. Right? The equation that he used to describe it, we refer to as the Arrhenius equation. What it says is that K is equal to A times the exponent of negative EA over RT. K here is called a pre-exponential factor. EA is the activation energy. And the way that we usually think about this is as follows. We're going to draw what's called a reaction coordinate. So energy is on the y-axis. On the x-axis, I have a reaction coordinate. This is some measurement of the progress of the reaction. So we start up here with our reactants. We end down here with our products. And what Arrhenius said was essentially there was a hill in energy that the reactants had to climb in order to form the products. The height of this hill is what we refer to as the activation energy. And this difference here between the initial energy of the reactants and the final energy of the products is what we usually associate with delta H. So this was Arrhenius's picture, right? And the way that this really sort of works is that this term here, I should start here. This prefactor is telling you about, for instance, the number of collisions per second, right? How many times these molecules are colliding. And this factor here, the exponential factor, is telling you about the percentage of molecules which have enough energy to get up over this hill, right? So how do you back out these molecular parameters like activation energy and prefactors? Well, as you often seem to do, right, if I take the natural log of both sides, K equals, I'm going to write it this way, EA over R 1 over T plus natural log A. Right? I am going to plot natural log K on the y-axis, 1 over T on the x-axis, and the slope of this plot will be negative EA over R. Right? So pretty straightforward. This is how you can calculate these things. And I wanted to close with just one example for you. And it actually has to do with my own research lab. So this was an article published not so long ago, 2017. I guess I'll use this thing, 2017. And it was in the journal Nature Materials. It's from a group out of Switzerland, out of Zurich. And what they were making were these substances called nanoplatelets. Right? These are semiconductor crystals that are shaped like a plate. So they happen to be very thin along the Z dimension. This way, they're 1 or 2 nanometers, and very long in the lateral dimension, right? 100 to 200 nanometers. So sort of a cartoon of what it might look like. And down here, you have a TEM image. It's a little bit hard to see, but for instance, like what you're looking at there is the top of one of these nanoplatelets. And you can go through and you can make them. You measure an absorption spectra for the particles, and you find it has peaks. And the position of the peak wavelength, is associated with the thickness of the platelet. We'll learn more about this in quantum next semester. But the position of this peak, the wavelength of this peak, is associated with the thickness. And what's interesting is if you look at the position of this peak over time, it doesn't move. So here's after 5 minutes of growth, you can see a little peak here. Right? This one keeps growing in, growing in, growing in. At some point, you see some other little peak grow in, but they never move. Right? And this is over like 18 hours of reaction. What you might anticipate is that as these things are growing, they would get thicker and thicker and thicker and thicker and thicker in a continuous fashion. And if that happened, what you would expect to see is this peak shift to longer and longer wavelengths. It would move out this way. But it doesn't. It stays the same. And so that tells us that the thickness of the nanoplatelet is independent of growth time. Right? It only grows laterally. So why? And they did a bunch of experiments to figure this out, but I'll just cut to the chase. They say the nucleation barriers on the narrow facets, that is the edges, are smaller than on the wide facets, that is the faces. For example, on a 4 monolayer facet, it's reduced from 1.6 to 1.3 EV. This implies a much faster growth on the narrow facets, 3 orders of magnitude faster at the growth temperature of 200 degrees Celsius. So this small change results in a 3 order of magnitude increase in the reaction rate. And the larger point, right, is that small changes in activation energy can make a huge change in reaction rate. So small changes make a big difference. And this is the entire basis for catalysis. Right? This is what catalysis does, is it finds an alternative reaction pathway with a lower activation energy, and the reaction takes off. All right, I'll stop here, and I will see you in the next videos for a discussion of mechanism driving rate loss.